Hi everyone. Let's start. So is there any question about the assignment or the course or the project?
Yeah, I had a question about the assignment. Um,
Hi.
question number 2.
So okay,
Uh,
let me
yeah,
bring the
question number,
let me
yeah.
bring the assignment. Just give me a second. Okay, question number 2.
So question number 2, I'm struggling to find what the derivative of that mean standard error loss is. Just the way it's written is very different. Like I've looked online, a lot of people have different methods. They plug in y equals mx plus b, and then they'll take a partial derivative with respect to the y-intercept and with respect to x. And I've tried a whole bunch of different like methods, and I don't even know what direction you want us to go on this.
The thing it is you need to follow the approach as we have in the slides. So the thing is that you remember, so what is question 2 in the assignment? It says that let me bring it. Yeah, I think I can share. Okay, sure. Let me share the thing. Screen. No. Yeah, something like that. Yeah, so this equation, yeah, I think, just give me a sec. Okay, this equation, so this is 1 over n summation fi x, right? I from 1 to n. This is what we had in this slides for, I think it was in the here.
Yeah, that's correct. Yeah.
Yeah, exactly. Let me bring this. Where was that?
Before this.
Yes, here it
Yeah,
is.
here.
Here, equation 31. So n here is 4. We have 4 points, and for each of the points we have fi. So we have f1, f2, f3, and f4 here, and x is the optimization variable. Here, for example, if you assume it is a neural network with 1 layer x, and also without any activation function. So you are saying that for the input data AI and its label LI, which you have provided here, so we have this FI for each of them, and now solve the 3 things: full gradient descent, stochastic gradient descent, and mini batch gradient descent. For full gradient descent, you need to calculate the whole gradient. How? Here we have it. No, sorry.
Oh, but for the derivative of
Yeah.
AIX minus LI,
Yeah,
because it's the mean standard error, you have
okay.
X and Y in the equation. So you have 2 partial derivatives.
For
You have
what?
to take
For so, why do you say partial derivative? I still don't get it.
because it says mean, like it's the mean standard error. So
Yeah.
you have input
So
minus output, and the output is with respect to Y. So you have to take the derivative with respect to X and the derivative with respect to Y.
No, Y is not a variable. Why you mean L here, right? L is not a variable. It's an input. So both AI, so we have pairs of AI, Li as data. These are not variables that you should opt. The only variable is X here. So see, this is Fi of X. So the optimization variable is X. And as you see here in this slide, you are minimizing over X. So
yeah, I think if that's the approach, then that's fine. The question's actually not that hard. It was just when I went online and tried to find similar questions, they Yeah, they were just much more complex and used partial derivatives.
No, no,
And
no, no, I didn't make the assignment complicated. It's so very easy. I tried to make it easy. So the only thing is that for full gradient descent, you need to use this full gradient. For a stochastic gradient descent, you need to use this. So see, it's already in the slides. So, and I have told you which eye you should choose. For the mini
yeah,
batch,
no, I had looked
for
up
mini batch, you need to use
like
this.
I know how to do the full gradient mini batch and
Yeah.
stochastic. I just
Yes.
couldn't get the original derivative because I didn't know the direction to go.
Yeah. Okay.
That's
Yeah.
also okay, but
Okay.
I think you cleared it up now.
Yeah. Okay. Great. Is there any other question? No? Sorry. Let me close this. Okay. So if there is no other question on the assignment, let me briefly tell
Actually,
you.
Ben, I have
Yeah.
one doubt.
Yes. Okay. Tell me.
For the coding part, is it okay if we use Keras library?
It's better to use PyTorch, but if you want to, let me think. Do you know why I'm not happy with the Keras much? Because it's very high level, so you don't practice coding much. It's just a ready to use function. That's why I want you to because I explained to you the code, right? I explained to you. Let me bring the code that we had. Even we had it in the slides. Here, line by line, I explained the code, the reasoning behind everything. So the reason that I want you to code is that so you use this code, you modify it a bit, but in this modification, you learn what each line is doing. That's a practice. That's why I'm asking you to use PyTorch. Is that okay?
Yeah, okay. But actually, I have used Keras previously, so that's why I asked.
Yeah, I understand. Okay, let me think. That's fine. If you think you're more comfortable with Keras, that's fine. Okay, sure. You can use Keras, but if you want my opinion, I think if you do the PyTorch thing, you will learn more. But if you want to do Keras, that's fine. And if TA doesn't give you grade for that, let him know that I said that's okay. So you can claim your grade for that. That's fine.
Okay. Yeah, thank you.
No problem. So any other question? No? Okay, great. So let me continue. Before we start, I want you to, because there was one part which I had doubt when I was explaining, I want to mention it very fast. So that was correct. So here we were, I was having doubt for proximal mapping of L2 norm. We are saying that, okay, now that we have this, so here, what is this? This is for this part. This is x over L over second norm of x over L. And yeah, I think something like that. But there is I believe there must be a squared here because so when I calculated, I got this. So when this will be this. When you have squared, you will have L squared then in the numerator. Then when you cancel it, you will have L over L2 norm of x. That's the reason. So that was one doubt that I wanted to clear. Now let's review very fast what we had for Newton's method, and then we will continue with the second order optimization. So very fast, if I want to review that. So we started with Newton-Raphson root finding method, and then we said, okay, rather than saying finding the root of f of x, let's find the root of gradient of f of x because of the first order optimality condition, which was this. And then we said, okay, then we derived the Newton's method for univariate optimization algorithm, and then unconstrained optimization. And then here we said, okay, let's have it for the multivariate by using the Hessian matrix, inverse of Hessian matrix. Then we said, okay, we justified it and said we said that the update in the Newton's method can be written either as equation 7 or as equation 8. Then we went to Newton's method for equality constraints. We said, okay, what if we have equality constraints? For that, we said, okay, let's consider the next step in the optimization. And then we formed the Lagrangian, then second order Taylor approximation. The Lagrangian again, we put it there. We worked it through using the KKT conditions, and then recall the KKT conditions that we discussed, and then we came up with this. So it's a linear system of linear equations. So using that, we can find P, which is delta X in the update of Newton's method. So we can handle equality constraints in Newton's method. And then we said also it can handle starting with non-feasible initial point, and if the optimization is a convex optimization problem, we know that after the first step iteration, all of the iterations will be feasible. So we can handle non-feasible points in the Newton's method as well. Then we said, okay, let's consider the general case. So let's add inequality constraints too. If we want to do that, then that would be the general case, which is mostly used in many optimization toolboxes such as CVX, and that's called interior point method, also called barrier methods, also called unconstrained minimization technique or sequential unconstrained minimization technique. And then we said the technique was having the inequality constraints as an indicator function, which is a regularization term for the objective function. And then this becomes an equality constraint optimization problem, which we discussed in previous slides, how to solve it. So we know how to solve this. But we said that, okay, this indicator function, which will blows up to infinity when its constraint condition is not satisfied, we cannot implement it in computer. Therefore, we need to approximate it. So we we approximated with a logarithm function, and that's why we have a logarithmic barrier or log barrier. So we have other approximations too, and those are different. So we have several barrier functions. One of them is log barrier. And why is it called barrier? Because from the point at which the constraint is not satisfied, the inequality constraint, it works like a barrier. It doesn't let this go. It's like a barrier. That's why the interior point method is also called barrier method. And we talked about this, and we said that, okay, its accuracy is good enough. Its minimum value is sandwiched between the actual minimum value and actual minimum value minus something. So the minimum cost function that it finds is better than the actual minimum cost function, although we usually want X star. F star might not be necessarily the case with what we want, but that's fine. So it's good enough. The interior point method, the log barrier, specifically this is for log barrier. Log barrier works well. Then now we start here. We continue the second order methods. Any questions so far? No? Okay. We continue with the second order methods by line search in Newton's method. So we talked about line search in first order methods. Now let's talk about line search in second order methods. Here we say, okay, we introduce Wolfe conditions. If you remember, when we were introducing line search and backtracking line search, also called Armijo line search, we said there is also Wolfe line search or Wolfe conditions, but we usually use that for second order methods, and we will study that. Here it is. So the line search for second order optimization usually uses checks two conditions, and these conditions are called Wolfe conditions. Wolfe was a scientist in optimization. So we use Wolfe condition to find the step size. Of course, line search is for finding the step size, for the learning rate, right? And at iteration k, we call the step size eta k. So now we say, okay, do you remember this? This is the update or delta x at iteration k. Recall this equation. Equation 7 or equation 8. So equation 7 delta x would also denoted by p. So minus Hessian inverse times gradient. Here we are repeating it here. Okay, now the Wolfe conditions are equations 25 and 26. So by the way, these are gradient of f. So pk transpose gradient of f and pk transpose gradient of f. So here these are two. You can see that it's very similar to what we had in Armijo line search. So that's why the first condition is the Armijo condition, and the second condition is called the curvature condition. And what are they? By the way, C1 and C2 are two scalars between 0 and 1, not including 0 and 1. And C1 should be very small, and C2 should be close to 1, according to reference 12. I think reference 12 is Nocedal's book, because Nocedal and Wright's book discusses Wolfe conditions and Quasi-Newton's method very well. So, first condition is called the Armijo condition, because we had it also in Armijo line search or backtracking line search, if you remember, in first order methods. The second one is introduced here as a second condition in the Wolfe condition, and that's the curvature condition. It ensures that the step size decreases the function slope sufficiently. By the way, the first condition, which is the Armijo condition, it ensures that the step size decreases the function value sufficiently. The curvature condition makes sure that the approximation, this is important, the approximation of Hessian remains positive definite. So how do we know that? Because if we choose the learning rate randomly, well, how do we know that the Hessian matrix, the approximation of Hessian matrix that we use in Quasi-Newton method that we'll see in a few slides, how do we know that it remains positive definite? Because we know Hessian matrix is positive definite. What do I mean by positive definite? I mean its eigenvalues are positive. So our approximation of Hessian matrix, which we'll introduce in Quasi-Newton's method in a few slides, should also remain positive definite, and this curvature condition makes sure that it is the case. And Armijo condition gives an upper bound for eta. This is determined by Armijo condition, and the curvature condition gives the lower bound for eta. So they sandwich eta. So they give a range for eta, an acceptable range for eta. Okay, now I have repeated the Wolfe conditions again here, just to say that there is also a strong curvature condition. So this is the weak curvature condition. But if you want to be more restrictive in the Wolfe conditions for line search, we can use the strong curvature condition, which is harder. Do you remember, for example, Armijo line search was harder or more strict than the simple line search. Also here, we have a strong curvature condition, which is harder than the weak curvature condition mentioned in equation 28. And also the Wolfe conditions can be used also for line search in first order methods, not They are not just for the second order methods, but they are usually used for Newton's method, for second order methods. Okay, so now we know how to find the learning rate in the second order methods. How we start with, for example, eta 1, and we halve it until we satisfy both of these equations. Or if we want to be more restrictive, to satisfy equation 27 and 29. So as long as the eta becomes small enough to satisfy these equations, that's done. We can choose that. Please feel free to ask me if there is any question. Fast solving of equations in the Newton's method. Do you remember in previous session, I also said that this in the interior point method and Newton's method, when we have this, we can make it fast, because for large dimensionality or large number of constraints, these matrices become large, and solving equation 16 might be time consuming. But in the optimization toolboxes, they usually use some techniques such as Cholesky decomposition and these things in order to accelerate that. I said that in the previous session, and I said Boyd also discusses that in his optimization 1 course. So here we are gonna briefly mention that. Okay, here. So there are ways to for fast solving system of equations in Newton's method. We are reviewing them. So by the way, in unconstrained Newton's method, we saw that this is the update. Do you remember equation 8 or equation 7? Let me bring it so you see, recall it. So we said either equation 7 or equation 8, they can be the update for the delta x is the update for the unconstrained Newton's method. Also, this is for unconstrained. For constraint, we also saw in equation 14 that we need to solve this system of equations here. Let me bring it here. We saw that, or if it is infeasible point, we need to do equation 16. So it's a system of equations, linear equations actually. And so either it's, and also when we have inequality constraints, we convert it to equality constraints using the indicator function or the barrier function. And then we use the equation 14 or 16 again. So either it is, no matter whether it's unconstrained or constraint with equality constraint or inequality constraint, we always have a linear system of equations, right? So we can write this linear system of equation as this. So Z here is standing for P and nu. P is the delta x and nu is the dual variable. Here we only have delta x. So Z here represents delta x. So either in here, Z represents P and nu, concatenation of them. Here it represents delta x, and M here, this is M. This is the coefficient of the Z. Also here, this is M. Q, this is Q here. Sorry, this is Q here. Here also Q is this minus gradient of F. So we always have something like this. Now, and our what we want to find is Z, right? Here we want to find delta x. Here we want to find delta x or P and nu. So we want to find Z from this linear equation. And by the way, M is a matrix, Z is a vector, Q is a vector, right? Now let's how to solve this system of equation, MZ equals Q, how to find Z fast. Note that when the dimensional, so the dimensionality of P here is D, is the dimensionality of D, right? When the X is in D dimension, a D-dimensional vector, then delta X or P is also a D-dimensional vector. What about nu? The dimensionality of nu is the number of constraints, equality constraints. Assume, I don't know, you can call it Q, whatever. So when, for example, here, 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 or here, or here. Assume A is Q by D. Yes, I think I'm right. So then it means that you have Q number of equality constraints. So B also is a Q dimensional vector, and X is a D dimensional vector, right? So if the number of constraints is Q, then the dimensionality of nu is Q. So here the total dimensionality of Z is D plus Q. Here the dimensionality of Z is just D. It means that Z is either D dimensional or D plus Q dimensional, right? And what does it mean? It means that when the dimensionality of data increases, if we have a huge number of dimensions in the data, or if we have a huge number of constraints, equality constraints, or both, then these we have a lot of these matrices here in this linear system of equation. They become very large, and solving this will be difficult. Therefore, we need to make it fast for huge dimensionality and the huge number of constraints, because in industry we usually have a lot of constraints. Assume you are you're optimizing the aerodynamic of I don't know, airplane. You know, you have a lot of constraints, So you have to make it fast. How? Let's see. Okay. We can use several techniques. One of them is decomposition methods, and decomposition methods also we have several decompositions methods. One of them is LU decomposition. So LU decomposition. So what does decomposition means? It means that when we have a matrix, we can decompose it into the multiplication of several matrices. So we have many decomposition algorithms, some of which are these. For example, one of them you were introduced to that singular value decomposition. In several sessions ago, I talked about it. One of them was eigenvalue decomposition, which I said the singular value decomposition and eigenvalue decomposition are related to each other. One of them is LU decomposition introduced here. So soon you have so in the MZ equals Q, the coefficient matrix M here, where for LU decomposition, let's have the LU decomposition of the matrix M. And LU decomposition is this PLU. So you decompose M into P times L times U, and L is a lower triangular matrix. It means that it's like this. So it's 0 here and not 0 elements here. U is upper triangular, means that it's like this, 0 here. And P is a permutation matrix. It means that it has 1 in each column, and in each row it has only 1, and others are 0. So and this P permutes the columns and rows of L here. So here, if we decompose it into PLU, there are some algorithms for this decomposition. You can say that, okay, I put this replace M with PLU, then I can say UZ, I can take it as W2. I can take LW2, which is LUZ, as W1. I define it, and then I solve this linear system of equation in this order, in these steps. I first do the LU decomposition of M, and then I do the permutation. So I calculate PW1, because here we have P times W1 equals Q. So I solve this to find W1. Then after that, so when I have W1, I solve this LW2 equals W1 to find W2. Then when I find W2, I put it here. So I solve this to find Z. I wanted Z, do you remember? Z was either delta X or delta X and nu. So you might say, why is it faster than solving this? because it has a lot in each of these steps. We either are working with lower triangular matrix or upper triangular matrix, or a permutation matrix which is very sparse. So it's very fast to solve this. Okay. Another thing, by the way, if you see the modern optimization toolboxes such as CVX developed by Stanford and Boyd, they always are using these decomposition methods in their codes. If you dig into their codes for the they are usually using interior point algorithm, and in that they are using these decompositions. You might see Cholesky decomposition specifically in their toolboxes. So here we are talking about Cholesky decomposition. So by the way, Cholesky decomposition is only valid for positive definite matrices, but we know that M is a positive definite. Why? Why is M positive definite? For example, here, because one of the, do you remember MZ was equals Q? One of them was for this. When we have, for example, unconstrained optimization. And we know that M here was the Hessian, and we know Hessian by definition is a positive definite matrix. Therefore, I want you to be sure that M is positive definite. Here, for example, is equal to Hessian. So we can, it's valid to decompose it by Cholesky decomposition. And then what is Cholesky decomposition? It decomposes into LL transpose, where L is a lower triangular matrix. And that's interesting. So let's replace M with LL transpose, and let's take L transpose Z as W1, and MZ equals Q is the equation. So let's define W1 as L transpose Z, and let's do it in this order. First, do the Cholesky decomposition of M, and then solve LW1 equals Q to find W1. So I find W1, and then I put W1 into this equation to get Z. And these steps are fast because they are working with lower triangular matrices. If assume M is a dense matrix, a dense positive definite matrix, it's very hard to solve this, very time consuming to solve this equation, especially when we have a huge M, but it's faster to do it here. Any question? No? Okay. Short decomposition. Short, by the way, can you hear me properly?
Yeah.
Can you hear? Yeah, great.
Yes.
Okay, great. Thank you. So short complement is also very mostly used in optimization toolboxes. And what is that? So when we have MZ equals Q, now let M be block matrix. So we have, it can be assume that the matrix M, you divide it into several blocks, M11, M12, M21, M22, and each of these is a block. So you have sub matrices inside this matrix, and you also can divide Z to Z concatenation of Z1 and Z2, and also Q to concatenation of Q1 and Q2. Okay, let's do this. So when we multiply this matrix into this vector, we'll have these two, M11 times Z1 plus M12 times Z2 equals Q1. Also M21 times Z1 plus M22 times Z2 equals Q2. So if we rearrange this, so we bring this to the right hand side, and we left multiply the sides by M11 inverse, we'll get this. Now let's substitute this Z1 into this equation to get this. So M21 times this plus M22 Z2 equals Q2. And then what are we doing here? Okay, let's factor out Z2, and also bring the term which doesn't have Z2 to the right hand side. So we'll have this. Okay, this term, forget about this. This term, which is multiplied in by Z2, is a Schur complement of the block matrix M11 in matrix M. So this was a block matrix M11. This is called the Schur complement of M11. Okay. and Schur was also a scientist. So we assume that the block matrix M11 is not singular. Why? Because we have M11 inverse. So we assume it's not singular, and so its inverse exists. So we can take, otherwise it will throw error when you are coding that. So then we can solve in this order. Calculate. So I want to calculate the Schur complement. So calculate M11 inverse M12 here, and then also M11 inverse Q. Why? Because we have it here. So we calculate these two terms, then calculate M tilde. So what is this? M22, M21, M11 inverse M. So this is the Schur complement. So we call it denoted by M tilde. So calculate this, but these parentheses you already calculated in the step 1. Here also calculate Q tilde, which is the right hand side of this equation, and in parentheses we already solved it in step 1. Then so we have the left hand side except the Z2, and you also have the right hand side. So now you have this. Solve this in order to find Z2. Now let's put it here back to this equation or this equation, right? Well, if you bring this to the right hand side, you will get this. So in order to find Z1, if you do this, you will see it's much faster than solving MZ equals Q. Why? Because you're using the characteristic that M is a block matrix. And you're using the Schur complement of this M11, and that's interesting. Okay, now it's over. The decomposition methods are over. So that one way to solve the Newton's method fast was this. Another technique is conjugate gradient method. You hear it a lot in optimization. I'm introducing it here. So conjugate gradient method, it was proposed in 1952. It iteratively solves equation 30, which was mz equals q, faster. So conjugate gradient method is for accelerating. It's just a technique for accelerating acceleration in solving a linear system of equations. It might not be necessarily used for optimization, but you can use it in other cases too. But here we can use it. Why? Because we have a linear system of equations, mz equals q. So it makes it faster and than the regular solution. Its spacing shows off better when the matrices are very large, especially. A good book on conjugate gradient is chapter 2 of the book, reference 17. You can look it up. And also truncated Newton's methods. There are some methods named truncated Newton's method. They also approximate the Hessian for large scale optimization. They usually use conjugate gradient as their approximation method for calculating the search direction. So it is widely used in different algorithms in optimization, such as truncated Newton's methods. Okay, but I'm not gonna introduce these methods in this course. You can look it up later. So the solution to equation 30, which is mz equals q, should satisfy this. Do you agree? When we have mz equals q, so left multiply the sides by m inverse, you will get this. And the conjugate gradient method, what does it do? It approximates this solution. So it's an approximation method, okay? But its approximation is accurate almost. It's good enough. According to the first order optimality condition, we know that as we learned in high school or college, the gradient at the extremum should be 0. Right, at the minimum here should be 0, and so the solution to equation 30, which is mz equals q, minimizes these functions. Why? So we know that the gradient should be 0. Therefore, mz minus q. We know that I'm rearranging mz equals q to become mz minus q equals 0. And then I'm writing it here, and I'm saying, okay, here I want mz minus q to be 0. Also, I know that the gradient of f of z star should be 0 because of first order optimality condition. Therefore, my gradient of f of z should be equal to mz minus q. Therefore, I'm doing the integral, inverse of derivative. My fz must be 1 over 2 z transpose mz minus z transpose q. There might be a constant too, but I don't care. So when you take the derivative of this, you will get this, right? So now I have this fz, this. Okay, now be patient and you will see how it's done. Conjugate gradient iteratively solves mz. It is an iterative algorithm. So it iteratively solves mz equals q as this. So you can see that it reminds you of the gradient descent algorithm. It's very similar to that. By the way, it's gradient ascent. Do you know why? It has plus, not minus. Okay. And it's very similar to the optimization itself. So it has an optimization in itself, apparently. Now, it starts by moving toward the minus gradient as a gradient descent does. Why? Give me a second, you will see. So then it uses this conjugate, the conjugate of gradient. This is the reason then for the name of this method. Okay, we'll see. At iteration k, the residual or error for fulfilling equation 30, which is mz equals q, is this. So what is this? We say that we want mz minus q to be 0, right? Here, I wrote it here. You can also write it q minus mz to be 0, right? So you want this to be 0, but as it is approximating that, and it's doing it iteratively until convergence, it's not exactly 0 at, because of approximation, also as because it is iterative algorithm. Therefore, you have some residual or error, and this residual is q minus mz. Ideally, this residual or error should be 0. And this residual, according to the equation 31, this is minus gradient of f of z. And if you see, okay, now I want to find the difference of residuals in between two iterations, k plus 1 and k. Let's see. Rk plus 1, according to this definition, is q minus mz k plus 1. Here we also have, according to this, I have this. So Rk is q minus mzk, but we have minus here, therefore it's minus q plus mzk. Okay, these two q's terms cancel each other, and I'm also substituting equation 32 for zk plus 1, and then these terms become based in terms of zk. And also these two cancel each other, so we'll have this. So the difference of residual is this between two iterations. Okay, now the initial direction, initially the direction is this residual. So the direction for the here, because it needs to, I'm deriving this pk in the conjugate gradient algorithm. So initially it uses this minus gradient. And when I said it's gradient ascent, I made a mistake. It's gradient descent. Why? Because this plus, it also has minus here. So it's minus eta gradient of f. So, so it's gradient descent. Sorry about my mistake there. So, and if you see that, if you replace this here, it becomes zk plus 1 equals zk minus eta gradient of fz. What is it? It's exactly gradient descent. So it's in its initial step, it is gradient descent. So it is using gradient descent in its initial step. But later, it uses another. It uses another equation, which I'm gonna explain for other iterations. For initially it uses gradient descent, but in the next iterations, it uses another equation. Okay. Also, it finds eta by it wanna find the best learning rate for its update here in equation 32. For doing that, it takes derivative of fzk plus 1 with respect to eta k. So it wants to find the best eta. For doing that, it takes the derivative and set it to 0, as we do it in high school, right? According to the first order optimality condition. And if you do that, eta k becomes this. And according to equation 33, because the residual was q minus mzk, so you can replace this with rk. This is the equation. Sorry about that. Yeah, this is the equation for the learning rate in conjugate gradient. Okay. Again, don't confuse this with the optimization itself. Optimization has its own learning rate found by Wolfe condition. There is another optimization for a conjugate gradient, and conjugate gradient is used for accelerating the Newton's method. So the acceleration method for Newton's method is using optimization in itself again. And eta is found by this. In its initial step, it's using gradient descent, and it's in its next steps, it's using equation 34. I'm not bringing the proofs here because it makes the course very complicated, but I'm introducing them to you so you know what these are. So pk plus 1 is the linear combination of rk plus 1 and pk. So again, you can see it is logging. It is logging the history of pk. Again, reminds you of the idea of momentum. As I said to you, usually the ideas in optimization are shared between the algorithms. Here you can also see this. So it's using the log of previous step, update p. Also, but it's using the residual. When the residual becomes 0, then you don't have any update. Why? Because beta is defined as this. As rk plus, so this is just rk plus 1. This is the numerator. R transpose R is squared L2 norm. And the denominator is rk squared L2 norm, right? So when R becomes 0, then this becomes 0, this also becomes 0, then the update is 0. So it means that you have the residue has become 0, the approximation is exact, the approximation of mz equals q is exact, and you don't need to update anymore. So you have found the good set here. You have found the best set. Okay. So it's solving for z iteratively. This is conjugate gradient method, and this is the algorithm. You can see here, this is the algorithm of conjugate gradient, which is called inside the Newton's method for solving mz equals q. How? So we have mz equals q as the input of this algorithm, and initially we use the minus gradient. In its initial step, it's just the gradient descent. And then in the next iteration, so eta is also we found it by taking derivative and setting to 0. And we also have here, this is the step of the iteration in the conjugate gradient. This is the residue which we calculate. If the residue is small enough, it means that the approximation is good enough, then break the loop, don't continue. Otherwise, you calculate this beta and you solve this p for this delta. P means delta x, right? Delta x, or here is delta z, because the variable here is called z, delta z. Do you remember here? Here, I'm talking about this. P is delta z here. So you are solving for z iteratively for approximating z. Approximating z, but in a good way and in a fast way. Okay. By the way, you don't, as I said also in my announcement, I understand that this might seem hard, but there is no exam on this. So with peace of mind, try to understand what I'm saying, because these are important concepts in optimization. I want you to be introduced to these algorithms, but there is no exam on this, so you don't need to worry about them. Okay, there is a relation of conjugate gradient method to Krylov subspace. Just one slide. If you don't understand this slide, that's fine. It's optional. It's a bit related to pure math, but I just want you to know that there is a relation between Krylov subspace and conjugate gradient method. And what is that? Okay, when two non-zero vectors x and y are conjugate, okay, I'm defining conjugate. If x transpose my equals 0 for an M which is positive definite matrix, okay? If we have this relation x transpose my equals 0, then x and y are conjugate. And that's why this is the reasoning behind the naming of the conjugate gradient method, because here we also mentioned it is using the conjugate of gradient. It is using the conjugate of gradient. That's why it's called conjugate gradient method, according to this definition. Okay, now we know that the order R Krylov subspace denoted by KR is spanned by the following bases. What do I mean by spanned? Span means that these are the basis vectors for this space. So a linear combination of these vectors make this space, and it's denoted by this. The solution to equation 30, mz equals q, should satisfy this. Do you remember that? Why? Because if you left multiply this equation by m inverse, you will get this. You will get this. And compare this with these bases. You will see that. So there is a relation between Krylov subspace and the conjugate gradient. The solution to the equation 30, which is using Newton's method, lies in the Krylov subspace. Okay, and the conjugate gradient method approximates this solution. It is approximating this solution lying in the Krylov subspace. Okay, and every iteration of conjugate gradient can be seen as a projection onto this Krylov subspace. We already talked about projection. Again, if you didn't understand this slide, that's fine. It's just optional. Okay. Now, nonlinear conjugate gradient method. Yeah. Okay. So as we saw conjugate gradient, so we talked about linear conjugate gradient method. Now this is nonlinear conjugate gradient. Let's see. Conjugate gradient is for solving linear equations, such as equation 30, which was mz equals q. But we have nonlinear conjugate gradient, NCG, which are very important and famous and well-known in optimization. What do? They generalize conjugate gradient to nonlinear functions. And recall this equation 30, mz equals q. So left multiply this equation by m transpose. You will have m transpose mz equals m transpose q. Then rearrange this, bring this to the left-hand side, you will get this. Okay? 2m transpose mz minus q equals 0. The goal of NCG is to find the minimum of this quadratic function. So what we were doing in linear conjugate gradient method, we said, okay, let's find this solution, the solution to this linear equation, system of equation, using iterative optimization, right? And it's a linear method. However, nonlinear conjugate gradient method has another approach. It says you want this mz to be q, similar to what we had in linear conjugate gradient method. I rearrange it to say mz minus q becomes 0. However, the linear conjugate gradient method called this residue, right? And it tried to find iteratively solve for z to minimize the residue. However, I say, okay, I minimize the residue in this way. I minimize its squared L2 norm. So this is the residue, right? But as you see, this is a quadratic function. It's not linear anymore. That's why it's called nonlinear conjugate gradient. Okay? So it's a quadratic, and it's using its gradient. The gradient of this function, what is the gradient of this function? Interestingly, if you take derivative of this, becomes this, you cite here. Oh, very interesting, right? So the NCG method is very similar to the conjugate gradient method, linear conjugate gradient method. But it uses steepest descent for updating its solution. You will see the, I think, yes, here we will see the algorithm of NCG. But let me introduce it here first. So it uses the steepest descent. We already talked about the steepest descent in first order methods. For finding the eta and for its learning rate. Do you remember eta is the learning rate for updating z? However, linear conjugate gradient method was using this equation for finding eta. I'm talking about their differences. The nonlinear conjugate gradient method uses steepest descent for finding eta. Also, it is using this equation the same as we had in the linear conjugate gradient method. So they are, in this case, they are the same. But it's finding beta in other ways. So we have several algorithms for finding beta. One of them is this, RK plus 1 transpose RK plus 1, RK transpose RK. So we can write it in this way too. We saw it for linear conjugate gradient method. So this is also used in linear conjugate gradient method. Recall here. But we can have other methods for finding beta too. And you can use any of these, and they become 0 when the residue becomes 0. So one of them is the beta 1 is called Fletcher-Reeves, proposed in 1964. The beta 2 is called Pollack-Rebier, proposed in 1969. The third one is Heston-Steffel, proposed in 1952. And the fourth one is Dai-Yuan, proposed in 1999. Again, these have proofs, but it's out of the scope of this course. So we have these betas and we can use them in our nonlinear conjugate gradient method. And by the way, beta 1 was used in linear conjugate gradient method. In all of these formulas, beta gets smaller if the residual of the next iteration gets much smaller than the previous residual. So when residue of RK plus 1 becomes much smaller than residue of RK, it's good. So beta, we can stop the optimization of the conjugate gradient method, and beta becomes very small, becomes very close to 0. Okay. Now this is the algorithm of NCG. So we initialize it by, again, similar to linear conjugate gradient method. In the first iteration, we do it by gradient descent. But in the next iterations, then we find P as a linear combination of the previous P and the residual. And the eta here is found by steepest descent, and Z is updated by this. We also had this in the linear conjugate gradient method. Again, done. Nothing very complicated. Any questions so far? No? Okay. By the way, this part, I agree, it's a bit theoretical, but I think from now on it becomes more interesting. Quasi-Newton's method, let me briefly mention that, and then we'll go to distributed algorithms, distributed optimization. I think that is very fun. We'll see that. Okay, so Quasi-Newton's method, what is that? Do you remember by the way, up to here, we were discussing how to solve Newton's method linear system of equation fast, which was mz equals q. Now we are changing gear to Quasi-Newton's method, and we'll see what it is. Here in Hessian, so in Newton's method, we have Hessian, right? Inverse of Hessian. Where was that? Let me bring it. Here, for example, we have inverse of Hessian, right? But if you multiply the sides by Hessian, then you will have this. You can rewrite it in this way, doesn't matter. So we have Hessian or inverse of Hessian, but calculation of Hessian is hard. It's usually hard and time consuming. Why? Because for Hessian, calculation of Hessian, you need to take derivative twice. But for gradient, you need to take derivative once. This might be the reason that many machine learning algorithms are using first order optimization. You might be wondering why backpropagation is only using first order optimization and not second order optimization. Why? Although we know that second order optimization is faster, much faster than first order optimization. So there are some advantages and some disadvantages for first order and second order optimization. That's important. Please listen to it carefully. So first order optimization, its advantage is that it's fast because you need to only calculate gradient. You don't need to calculate second order derivative. However, it's slow. Do you remember, especially the previous century, they said, oh, it's very slow. How can we accelerate it? And someone named Yuri Nesterov proposed accelerated gradient method in order to accelerate that, because first order methods are usually slow to converge. However, on the other hand, we have gradient second order optimization. Second order optimization is usually fast. It's if you look at their convergence rate, they're faster. They're much faster than first order optimization. However, they have a big disadvantage, and that's calculating the Hessian or the second order derivative. It is very hard. Why? Because you need to take derivative twice. Also, gradient, when your variable is a vector, gradient becomes a vector, but second order derivative, which is Hessian, becomes a matrix. Calculation of matrix is much harder than calculation of vector, right? If your variable is a matrix, the gradient becomes matrix, but the Hessian becomes a tensor. So usually by one order of dimensionalities, it's harder to calculate. So if it's a vector, you need to calculate matrix. If it's a matrix, you need to calculate tensor. So it's time consuming. Also, it's resource consuming to calculate Hessian. So this is the disadvantage. Maybe, this is my conjecture, that's the reason that second order optimization is not used much in machine learning algorithms and in many, maybe in industry, because it's hard for them to calculate Hessian. Okay, so that's one thing. And now Quasi-Newton's method says, okay, I understand you're tired of calculating Hessian or inverse of Hessian. Let me approximate it for you. So you don't. It's not very it's not very hard and tiring for you to calculate the Hessian or inverse of Hessian. Although it's an approximation, it's not exactly accurate, but it's good enough. Okay, let's do that. So similar to what we did in equation 6, do you remember in equation 6? Here, in equation 6, we did the second order Taylor approximation for f of x, and for justification of the Newton's method, the unconstrained Newton's method. Do you remember that? In previous session, we did that. Similar to that, we can approximate the function at the updated solution by its second order Taylor series. So for f of xk plus 1, the updated, so it's f of xk plus pk, because this is xk plus the update becomes xk plus 1, right? So we can have the second order Taylor approximation by this, and where p is delta x, the update. Here, bk is the Hessian. So you might be surprised that usually in the literature of second order Newton's method and second order optimization, in the literature of optimization, they denote Hessian by b, not by h. But they denote inverse of Hessian, b inverse, by h. At the first time that I saw that, I said, why do they do that? Still, I don't know the reasoning behind that. To me, it's confusing. But they use h to denote Hessian inverse, not Hessian. They denote Hessian by b in pure optimization papers. Maybe in some optimization papers which are not pure optimization, they denote Hessian by H, like in machine learning papers. I don't know, but in pure, if you look at the literature of optimization, you'll see that Hessian is denoted by B usually, and Hessian inverse by H. Okay, that's one thing which you should note. BK is the Hessian at the iteration K. Okay, so we can write gradient of f taking derivative from this equation. From this equation, I take derivative with respect to p. So this term becomes so this term is a constant, it goes away, constant with respect to p. This is linear with respect to p, so it becomes gradient of f of xk. This is quadratic with respect to pk, so it becomes bk pk, and 2 is cancelled by 1/2. So we have this. This is called the second equation in the literature. This is okay. Setting this derivative, I set this derivative to 0 for the sake of first order optimality condition, as we had in high school. Okay, so setting this derivative to 0 for optimization gives this. So we rearrange this, we bring this to the other side, and we'll have this. We can left multiply the sides by B inverse or Hessian inverse, and we'll have this, where H denotes the Hessian inverse. Okay, and where did you see that? We saw that in the initial slide of Newton's method. Equations 7. So delta x is p equals minus Hessian inverse gradient of f. I'm repeating it here, but with a new notation. Okay. Now note that, yeah, I said that already. Now we found this. Considering the step size p, we can write the step s. So I call that here, I say that p doesn't have eta in it. Usually up to here, I called p equals delta x, but now I'm separating them in this section. I'm saying that delta x, let it be denoted by sk, and sk equals eta pk. So pk, let it not have eta in it, okay? So s or delta x equals xk plus 1 minus xk, which is minus eta h gradient of f. This is the update in the Newton's method. Okay. Now computation of this Hessian matrix is very usually expensive. One way to approximate that at every iteration is conjugate gradient method, which we already discussed in previous slides. Another approach for approximating this solution is Quasi-Newton's methods, which approximates the inverse Hessian matrix or the Hessian matrix. Why? Because you can either use here, recall here again. If you are using this equation, you need inverse of Hessian. If you are using this equation, you need Hessian. So you need either the approximation of inverse of Hessian or Hessian. Okay. So we have this. What is it? They approximate the Hessian based on the step pk, the difference. So this is let the difference between the gradient of f at iteration k plus 1 and the gradient of f at the previous iteration be denoted by yk. It's a d-dimensional vector, okay? So what do the Quasi-Newton's method do? They are approximating the Hessian or the inverse of Hessian using these variables, using pk, which is the update, using the yk, so using this yk, the difference of the gradients, and using the previous approximated Hessian or inverse of Hessian. Again, the log of history. So they're using the log of history, the difference of the gradients, and the p, which is the update. Okay, let's see. Some papers approximate the Hessian by a diagonal matrix. Okay, for example, you can look at these papers. In this solution, what do? The inverse of approximating Hessian is simply the inverse of its diagonal matrix. Why? This is the reason. When you have a diagonal matrix, it's inverse. Let it be. Just give me a sec. They'd be A, B, C, and these are 0. Its inverse is this: A inverse, B inverse, C inverse. It's a lemma. You can see, look it up. When we have a diagonal matrix, its inverse is the inverse of its diagonal elements. So if you assume that Hessian, if you relax the Hessian matrix to be diagonal, then it makes it easy for you. Although it's not accurate, but its calculation becomes much easier because its inverse is just the inverse of diagonal. So they can, some pairs do that. Some methods use a dense approximation for the Hessian matrix, not a diagonal matrix anymore. Some examples are a BFGS algorithm or Broyden-Fletcher-Goldfarb-Shanno BFGS. This is the most famous Quasi-Newton method. It was proposed in 1987 and 1996, around those time. And these are the scientists who proposed that. Also, there is limited memory BFGS. This is also very famous. So these two are very famous Quasi-Newton's methods, proposed in 1980 to 1989 at that time. It's a simplified version of BFGS, which utilizes less memory, because at that time, it was the computers were coming gradually, and but they were not very powerful. So the memory was important at that time. So they were trying to design or modify BFGS in a way that it uses memory less. Okay. And some other Quasi-Newton's methods are like this: Davidon-Fletcher-Powell or DFP in 1987, 1991, Broyden method in 1965, and Symmetric Rank-one or SR1 in 1991. So you can look up their papers. In the following, we're reviewing this, and more explanation on these methods can be found in the chapter 6 of Nocedal's book. As I said, Nocedal and Wright's book, and especially in chapter 6, they talk about Quasi-Newton's method a lot. Okay, so here we define these two. So let rho k be a scalar defined as 1 over y transpose s. What was y? Here. Y was the difference of gradients. And what was S? Was delta x minus eta p minus eta Hessian inverse gradient. So 1 over their inner product, let it be rho k at iteration k. And also I define this matrix VK, which is a D by D matrix. And let it be the identity matrix. This is identity matrix minus rho YK. Again, Y is the difference of gradients, and SK transpose. SK is the update. S is the update. And these are vectors. So vector times vector transpose, it is a matrix. This is also identity matrix. This is a D by D matrix. You can write it in this way by substituting this row into this equation. You will have this. Okay. So I'm defining these two, and again without proof here, because out of the scope of this course, you can look up the proofs online. We have several algorithms. BFGS says that I approximate B in this way, and so this is the approximation for the Hessian, and this is the approximation for the inverse of Hessian. So either you wanna use Hessian or inverse of Hessian, depending on whether you wanna use equation 7 or 8 in Newton's method. Then you can use the approximation of Hessian or inverse of Hessian, and they are based on Y, which is the difference of gradients, and S, which is the update, and B, the previous approximated Hessian, or H, the previous approximated inverse of Hessian, and rho, which we defined here, and V, which we defined here. Based on these, they have some approximations. Proofs, you can look them up online. David or DFP algorithm also has some other things, but as you see, there are all of them are using rho, V, H, B, Y, S. They are using only these. Okay. Comparing equation 46 for BFGS and 47 for DFP shows that the BFG and DFP methods are dual of each other. You can see that. Why? Because this B is very similar to H. So B in DFP is very similar to H in BFGS. H in DFP is very similar to the B in BFGS. That's why they are dual of each other. And experiments have shown, according to paper 32, that experiments have shown that BFGS often outperforms DFP. Okay. Now, two other methods for Quasi-Newton's method: the Broyden method and a Symmetric Rank-one method. Again, they are using Y, S, B, H. They are not using rho here anymore. Rho and V. Rho and V were used in BFGS and DFP only. Okay. Now here, again, you can look the proofs online. These are famous algorithms, but BFGS and LBFGS, or limited memory FGS, are the most well-known Quasi-Newton's methods. Okay. Now let's talk about LBFGS a bit before we concluding this slide deck. So we talked about BFGS. Now it's limited memory version. The above methods, including BFGS, approximate the inverse Hessian matrix by a dense D by D matrix, right? What if we have, what is D? The dimensionality of variable X, right? What if we have a huge D? Then storing that in matrix is very memory consuming. So when you have inverse of approximation of inverse of Hessian, you need to store a D by D matrix. Or if you want to use the approximation of Hessian itself, you also need a D by D matrix. How do you store this matrix in memory of computer if D is large? You can't. You will have a memory error in your code. Therefore, they propose limited memory BFGS, LBFGS. It was proposed by Nocedal. Now you will see that why Nocedal has focused on that in his book, chapter 6, I guess, because he has contributed in that, and he's an expert in that field. So it was proposed by Nocedal et al. In 1980s. It uses much less memory than BFGS. In LBFGS, the inverse of Hessian is interesting. They don't use a D by D matrix for inverse of Hessian anymore. They approximate it by a scalar, multiply the identity matrix. So they just relax that, the inverse of Hessian, to be multiplication of a scalar, just a scalar to an identity matrix. Identity matrix, you don't need to even store it in the memory. It's identity matrix, a diagonal matrix with one as diagonal elements. So it's only one scalar. The information is one scalar. So that is this. So they say H, which is the inverse of Hessian, let it be gamma k I. Okay, but this is the initial H. So you are updating H in this way. But let's talk about it. So it approximates the D by D matrix by just a scalar. Okay, it uses memory of M previous variables. So it uses the memory of M previous. So the difference here is that here in BFGS, we are using the memory of only previous B or previous H, right? Only one memory back. But LBFGS says, let me use the previous of M steps back, more steps back, M steps. Okay, and let's recursively calculate. So it has a recursive. If you want to code it, you need to have a recursive function. So it recursively calculates the updated direction of solution. So in other words, it has recursive unfoldings which approximate the descent directions, or the P or delta X, in optimization in this way. The number of recursions is a small integer, such as 10. So they don't use a huge number of recursions. Why? Because when you have a huge number of recursions, you have another problem with the memory and in your computer, because the recursive function uses stack. in your memory. So it becomes very slow, very fast, like when you are implementing Fibonacci series, right? Using recursive functions. But they usually use small number of recursions, so they don't have the problem of a stack memory. So not much memory is used. By m times recursion on equation 46, what is 46? We have BFGS. So that's why it's limited memory BFGS. So they are having its recursion on this equation of BFGS, but m times, okay? The LBFGS approximates the inverse Hessian as this. You can look its proof online or in Nocedal's book. Okay, so it's this. So H0 is just a scalar times the identity matrix, and V was defined here in equation 45, right? So, and rho and S were also defined here. Rho was here. S was the update here, equation 42. So if you put this in this, and as you see, you have m times of recursions, but m is a small, and it uses much less memory because it's just a scalar. Okay, now I'm showing the LBFGS algorithm here. Why am I focusing on LBFGS algorithm? Because most modern optimization toolboxes, they're using LBFGS for the Quasi-Newton's algorithms. If you look at, for example, ManOpt, it's optimization on Riemannian manifolds. This is a toolbox. That also uses LBFGS a lot in its toolbox. So many optimization toolboxes are using LBFGS nowadays. So the LBFGS algorithm can be implemented as shown in the following algorithm. This algorithm is inspired by the algorithm mentioned in Professor Reshad Hosseini's and Subrit Sraz. Reshad Hosseini is in University of Tehran, and Subrit Sraz is in MIT. That algorithm itself is based on the algorithm in the Nocedal's book, in chapter 6 of Nocedal's book. So here, as this algorithm shows, every iteration of optimization calls a recursive function for up to m recursions and uses the stored previous m memory to calculate the direction p, or for updating the solution. Let's see. So as equation 41 states, the initial updating direction in Newton's method direction is this. It is the Newton's method direction. Okay, so H0 itself is a scalar times identity. Also, what was equation 41? Let's go back here. As we had here, for initial P, we use this. We use minus Hessian inverse gradient as we have in the Newton's method. So we use this. So let's see. So initially H is just a scalar times identity as we have here. Okay. Then we have the for loop for the optimization itself, and finally we return the solution. But inside this for loop, let's see what happens. This is LBFGS. So we get the direction. Let's go to the get direction. And this get direction, as you see, it's a recursive function. Why? Because inside of it calls itself for m times. And the criteria, the termination criteria for the recursion is m steps. That's why it doesn't go further than m, and returns that. And so we have rho here. We saw rho. Where did we saw that? Here. We defined it here. So we have rho. We have p tilde here. Then we are feeding that as the input to the recursive function, and we get p hat. Then we return p hat minus rho times this. If you work out this equation, you will get this, what you have here. So you need to work out this equation. And then, but initially it returns H inverse P, H0P, which is this. And then you have the update. You have the update. Here, what is this? Sorry. What is this S? S, we defined it here. Equation 42. It's exactly repeated in this algorithm. We have Y with the difference of gradients. We defined it here. Equation 43. And we have gamma, which we, I think gamma was the factor for a scalar in the Hessian inverse. And then Hessian inverse is that scalar times I. That's it. And then store it in the memory for m steps before. So this is the LBFGS algorithm used a lot in optimization toolboxes. And as I said, Professor Reshat Hosseini and Suritsra have used that a lot in their papers. If you look at that, especially in Riemann optimization, it's used a lot. So, okay, before we end this slide deck, let me tell you the acknowledgements. Some slides of this slide deck are inspired by lectures of Professor Stephen Boyd at the Stanford University, especially the part on the Newton's method, interior point method, barrier method, and those things, and also the parts on the fast calculation of the linear system of equations in Newton's method, like such as Cholesky and conjugate gradient and those things. As far as I remember, most of them were in the optimization one of optimization one course of Stanford. But maybe, I don't remember conjugate gradient, maybe it was in the optimization too. Some slides of this slide deck, especially the Quasi-Newton's methods, are inspired by teachings of Professor Reshat Hosseini at the University of Tehran, which I mentioned. Also, our tutorial has some materials in this slide deck. Let's very briefly review the references as far as I remember, because some of them I might not remember, but you can look them up where they were mentioned in the manuscript. So this is a book on optimization. This is a Nesterov paper, Yuri Nesterov, a famous scientist in optimization, on interior point algorithm. Again, in SIAM. SIAM is a very important journal for optimization. So we have interior point methods. Again, there may be a survey on that. The right. So Boyd, convex optimization of Boyd. Again, Wright has a paper on interior point revolution in optimization. See, it's a revolution. It was a revolution because it can solve general case optimization problem. It doesn't need to be linear programming. It doesn't need to be necessarily quadratic programming or something. It can be anything. Yeah. But if it's convex, it has some guarantees. If it's not convex, it's usually in practice it's good enough. Although it might not have some guarantees, but it's usually good enough. So Deakin has iterative solution of problems of linear and quadratic programming. Here we have sequential unconstrained minimization technique, which was another name for interior point method. Do you remember? Nesterov, the book of Nesterov, Yuri Nesterov lectures on convex optimization. Boyd et al. Have the toolbox CVX, which is a MATLAB toolbox, but it has also its Python version for optimization. One of the most well-known optimization toolboxes is the CVX. And this is our tutorial on optimization, which has the material here. Also, some Wolfe's paper in 1969, published in SIAM Review. Again, SIAM, a very important journal. Convergence conditions for ascent methods. This is Wolfe conditions. The paper for Wolfe conditions. Nocedal and Wright's book, Numerical Optimization, Chapter 6 talks about, I think Chapter 6 talks about Quasi-Newton's methods, BFGS, LBFGS, all of these. Nocedal proposed LBFGS. Armijo paper in 1966 for Armijo condition in line search. Also, we have an important book on matrix computations, which also talks about the matrix decompositions, such as Cholesky decompositions, LU, and these things. You can look up in Golub and Van Loan matrix computation. and in Johns Hopkins University Press. Also, we have the Schur complement and its applications. We talked about it. Methods of conjugate gradients. So in 1952, conjugate gradients that we talked about. Here we have, I don't remember what this was for and what is this servo truncated Newton's method. I said they also, I don't introduce it here, but they use, I think, the conjugate gradient method in them. Krylov subspace, do you remember Krylov subspace we talked about? 1931. This is the paper discussing the subspace. At that time, he didn't name that, but it was named after Krylov. And function minimization, conjugate gradient, here, 1964 by Fletcher and Rivas. And here, it's not a paper in English. It's in another language. I don't remember what it was for, but you can look up in the slides. Here, nonlinear conjugate gradient method. 1999 in SIAM Journal on Optimization, a very important. So we, as you see, we have several SIAM journals, and many of them are important for optimization. One of them is SIAM Journal on Optimization. One of them is SIAM Reviews, and one of so nonlinear dimensionality reduction. Also, we use that. I think this is a good book on dimensionality reduction. This is diagonal Quasi-Newton method. Do you remember I said some papers are using diagonal Hessian or diagonal inverse of Hessian for simplicity of calculation. Here, Fletcher, a famous scientist in optimization, it's a book. Also, so I don't remember this, but this one, Quasi-Newton's method. So these are the papers for the Quasi-Newton parts. So this is LBFGS. This is the famous paper by Nocedal and Liu in 1989, which proposed LBFGS, which is used a lot nowadays in toolboxes. This, I don't remember what this was for. So a class of methods for solving nonlinear simultaneous equations. Broyden. Do you remember Broyden's method and Quasi-Newton method? So these are the Quasi-Newton's algorithms that we talked about. You can look up in their papers, 1965, 1991. Convergence of Quasi-Newton matrices. This is also a paper. Nonlinear programming, this is a book. Now, and this is the paper which I mentioned, the algorithm of LBFGS from by Reshat Hosseini and Subrit Shah. It is in MIT. They have worked a lot on expectation maximization for, or an alternative to expectation maximization for Gaussian mixture models. And in those papers, they are using LBFGS a lot. If you can see, you can look at their papers. And that's it. Any question before the break, and then after the break we'll continue with the distributed optimization. Any question? No? Okay, great. So let's come back at 8:50, right? Yes, 15 minutes of break, and we'll continue. 8:50. No other question? Okay, great. So now we are gonna continue the session, but before that, I made an announcement in the course link saying that so we'll have the next session teaching, the next session after the next session. So it's in 2 weeks. The session will be used for your presentations. Okay. Until then, please try to do most of the work of your projects so you can present well your results, your project well. Until then, you don't need reports. The reports deadline is, I think I mentioned that. What was that deadline? I think it was, I'm not sure about it, but take a look at that. But I think it was March 14th, something like that. So
Yeah, it's the 14th.
yes, so great. So March 4, you will, April 4th, you will present And the order of presentations, the teams, I will just write a code to make random choices. So computer will randomly choose which order of teams to present, but all teams need to be present at 7 o'clock in the class time, and all students are supposed to be present because everyone should present in the course project, and every team needs to divide the time of presentation fairly between all the team members, and roughly 20 minutes, 18 minutes maybe for presentation, and 2 to 3 minutes for asking. Either other teams will ask or me, I will ask, and please don't take it adversarially. We are all friends. And when I or other teams ask, we are just asking for clarification, for understanding, for recommending how to improve your project. Okay, take it as a hint for improvement of your project, and don't take it as an adversarial thing or something like that. And yes, so I think I said everything. And according to our feedback, other students' feedback and me, you will have time until April 14th to submit your finalized report. And I think the deadline for me to submit the marks is April 26th, as far as I know, but I will submit it sooner. So you know your grades soon, and you don't need to worry about that, as it's a graduate course. 50% of the total mark is for project, so 40 is for report and project itself, and 10% for the presentation. That's why I'm saying that every student need to be present at that day to present, and that's for the 10% of the grade. Any question? No?
So Ben, is there any like the number of slides, like how many number of slides should be there? Is there any limit to it?
Your choice, but let it be
Okay.
restricted to 18 minutes of maybe 17 to 18 minutes of presentation, and leave 2 to 3 minutes for us to ask questions.
Okay.
Yeah, don't go over than 17 or 18 minutes of presentation, please. Otherwise, I need to stop you because the class time is limited. Okay. Yeah, and also, the template is yours for the presentation. Before the class of April 4th, you need to submit your slides as a PDF and in the course link as a part of your presentation mark. And also, but the template of report, I have determined that. So we have all the same template for reports, and the maximum number of pages, let it be 5, 2 columns. Okay. Everything is clear? Okay, and you don't need to worry about that much grading and these things. As long as you do a great job, a good job, you will get the 50% or close to 50% of the mark already by doing the project and presenting. So you don't need to worry about that. Again, my goal in my courses, this course and the courses in the next semester and this, so is this, my approach is this: I try to teach well enough according to what I think. Maybe my opinion is wrong, but I try my best to teach you well, with good quality, so you learn algorithms well, and different algorithms, so you become knowledgeable. But for grading and for assessing, I take it easy. Because I want everyone to enjoy the course. That's my goal. Because learning is fun to me. We need to learn in a fun way. We don't need to. When you, for example, learn something from YouTube, I want you to learn the courses that I teach in this way. When you look at the YouTube videos, for example, I look at YouTube videos of Stanford, like Boyd, or sometimes I look at their courses on physics, theoretical physics. I really enjoy that because there is no worry for me about the grading, right? exactly do the same thing here. Try to learn with fun, without worry for grade. Do your assignments, projects, and these things, and then so this is my approach. I try to teach well, in my opinion, and then for grading and these things, I try to take it easy. You don't need to worry about it. I'm not a hard taking instructor. Okay. Any question? No. Okay. So let's continue. Let me. Okay. Now, a fun thing. This is really fun, this part. Distributed optimization. Assume you have I will tell you what it means. So problem statement. Assume you have, we have several optimization variables. So rather than one optimization variable, let's have several optimization variables. M of them, xi, x1 to xm, okay? And each of them might be a vector or might be a matrix or something like that. So for example, x1 is a vector, x2 is a vector, by the way, they can be scalar because a scalar is a special case of vector, right? It's a one-dimensional vector. They can be matrix, doesn't matter. And another interesting thing is that their dimensionality might differ. For example, the first one might be three-dimensional, the second one might be a scalar, the third one might be 10-dimensional. As long as they are in their summation or in their linear combination, they are compatible. For example, you might have something like this. x1 transpose x1, and where x1 is a vector, I write underscore before this because I can't write bold in. Okay, assume it's bold. Okay, this is a vector, x1 transpose x1, but x2 let it be scalar, like x2 squared. Okay, x2 is a scalar, x1 is a vector. I don't know, maybe let x3 be a vector. So we have we have three variables, x1, x2, x3, but with different dimensionalities, but we can sum them. So because this is a scalar, this is a scalar, this is a scalar. So that's what I'm saying there. Assume you have a set of several optimization variables. We can distribute our optimization algorithm among these variables. And that's an interesting thing, right? Why? Because nowadays we have we need to make everything in parallel. We have a lot of parallel cores in CPU. And also we have a lot of freedom and also we have a lot of optimization variables because now that we have complicated computers or quantum computers, we can solve very complicated optimization algorithms in physics, in theoretical physics, or in I don't know, maybe aerodynamics. These are complicated optimization algorithm problems. So we can do that. Okay, so let the M be the number of optimization variables. Okay. In this case, we have distributed optimization because we can work on the optimization variables in a distributed manner. Okay, now let's see, alternating optimization. Okay, consider the following multivariate optimization problem. Minimize this optimization problem. Again, the cost is a function of m variables, x1 to xm, where the objective function depends on m variables. When we have several optimization variables, we can alternate. So this slide is about alternating optimization. This is one of the approaches. So we have several optimization algorithms for distributed optimization. It's a family of methods. One of them is alternating optimization, introduced in this slide. And this. When we have several optimization variables, we can alternate between the optimizing over each of these variables. This technique is called alternating optimization. You can see paper 1 or chapter 4 in book 2. So alternating optimization, what does it do? It alternates between updating every variable. So updating every variable while assuming other variables are constant. That's an interesting thing. So see here, for example, x1, you minimize function f with respect to x1 But for the other one, the other variables are just constant, considered constant for this. Why? Because this optimization problem in this line is just with respect to x1. It's not with respect to x2 and x3 and so these are just constants. And what do I put for these constants? I put their value in the previous iteration. So now I'm in k plus 1 iteration. What is their value in k iteration k? I put that. And then I minimize this function. So this is a function of variable x1, because these are just, I put the values for these constants. Now it's just a function of x1. Now minimize that. The argument will be, the argument of this optimization will be x1, right? I do the same for x2. However, note that for the other ones, again, I put the constant, for these constant variables, I put their previous value. For x1, now I can put this updated x1. I don't need to put x1k. I can put x1k plus 1 because I just updated x1. Why do I use the previous one? Right? So when you go until the last one, one by one, you are using just the variables which were just updated before them, before this line. So this is what you are having, and you, after this line, you do it, you go and do it again. So you have a for loop. So for this, a for loop, a loop, you do this and then this and then this and then this, then we do it again. So it's iterative. So in each iteration, in each, do you remember in gradient descent, for example, in each iteration we had one update. In I think accelerated gradient method we had two updates. Here in alternative optimization, the number of updates is the same as the number of variables, because we need to update m variables, right? And so this is minimization with respect to x1. This is minimization with respect to x2 until this is the minimization until with respect to xm. And you can see that this, okay, this is the thing that I wanted to, by the way, what can I do for argmin f here? Can you give me some examples? What is your suggestion? So I want to consider only this line. I want to do this. What are your suggestions? Could you please let me know? I'm waiting for your answer. You can say anything. It might be wrong. That's fine. Please say. I want to find minimize function f with respect to x1. What can I do?
We can integrate it.
Integrated what for what? You mean take integral?
Yeah.
Why? Can you elaborate?
Yeah, because I think in order to find the minimal of any function, we can, like the basic approach is to just integrate it.
You mean there? I think the other way around.
Oh,
You need to
derivative.
take
Yeah, sorry.
derivative.
That derivative. Sorry, my bad. Yeah.
Yeah. So one thing is that yes, take derivative, set it to 0, right?
Yep,
You mean that?
Yep.
But what if you don't get the closed form solution? Of course, the first thing in optimization, which should come to your mind, which should come to your mind, if the problem is unconstrained, here it is unconstrained, right? Is taking derivative, set it to 0. If the solution is closed form, it's done. It's like high school, right? But what if you can't isolate x in one side of the equation and the other parts in the other side? So what if you can't take it? It's very complicated and you can't have iterative a closed form solution. Then what should you do? Can you tell me? Can anyone say? So what you should do is exactly what we learned so far. You need to do iterative optimization, right? So in optimization, either you take derivative, set it to 0. It's closed form, it's done. If not, you need to do it iteratively, like numerical analysis, what you do in numerical analysis. You have for that, you have either first order methods or second order methods. We talked about first order methods. It's either gradient descent or proximal methods or accelerated gradient methods or stochastic gradient descent or minimax gradient descent, or many things. Do you remember? Or proximal methods. You can use those, or you can use second order optimization, like Newton's method, right? The things that we talked about. So each step here is an iterative optimization. It's a first order optimization until convergence because it's argmin. Do you get it? So for example, each step can be a gradient descent until convergence. Is it clear now? Can you please tell me?
So we take a iterative approach and minimize it, like take it to convergence and minimize it in every iteration.
Yes. However, so you have a convergence here for x1k plus 1, convergence here for x2k plus 1 until here, but you also have a convergence for the alternating optimization. Your x1k plus 1 should and x1k plus 2 shouldn't change much. This until convergence is for the whole alternating optimization. But in each line, as it is argmin, you need to solve it however you want. You can use gradient descent. You can use Newton's method. If it's closed form, you take derivative, set it to 0. You get my point? As it is argmin, you need to do it until convergence. But when I say until convergence, I mean roughly until convergence, right? Not you might not reach completely to that. Is that clear now? Yes? Okay, in the comments. Yes, okay. Now that I said to you, this is the ideal. This is the ideal theoretically. In practice, now listen it from me, which I have done it a lot. In practice, usually if you do it only one step at each iteration, for example, one step of gradient descent, or one step of proximal method, or one step of Newton's method, and also do the whole thing for until convergence. So you don't do every step until convergence, but you take care of until convergence for the whole alternating optimization. But you do one step for each iteration for each of these. In practice, it works. So in theory, as it is argmin, you need to do each step until the end. But in practice, listen to me, you can do one step. It usually works. You get my point? One step of gradient descent or something like that. Okay. Okay, now. By the way, it's usually robust to changing the order of updates. One might wonder, okay, we have order, but it usually is robust to the changing of in the order of updates. Okay, now alternative optimization for decomposable functions in terms of variables. So assume we have this summation of fi xi. Assume you have summation of, so now f is a summation of fi's xi's, okay? We saw similar thing in a stochastic gradient descent. Do you remember? Okay, so then the alternating optimization is simplified to this. Now, why? Because the other terms of, for example, when you are minimizing with respect to x1, f2, f3, f4, they are all constant. So you can drop them. For x2, f1, f3, f4, they are constant. So it will be simplified for decomposable function. Okay. And the above updates mean that if the function is decomposable, then we can do that. Okay. So hence, alternative optimization is reduced to m independent optimization problems, each of which can be solved by any optimization method, such as first order method or second order method. Okay. Now let's talk about it. Proximal alternating optimization. It says that, do you remember proximal operator we talked about? Do you remember that? Okay, for minimization to keep we can use this in each, do you remember I said in alternating optimization, in each of these, you can use any optimization algorithm that you want. You can use proximal operator for the, like what you had in proximal gradient descent, I think. Proximal gradient method. Do you remember we had that? So you can write it in this way, and you can say that, okay, I want to minimize this function. Again, I use these as constants only with respect to x1, and here with respect to x2 and these things. I also add this. Why? Why do I add this? Because I want to do the proximal mapping. So this, for this term, I can add this. I can add this, and this becomes a proximal mapping. So at each step, I can do a proximal mapping. Again, you need to do it until converges theoretically, but in practice, even one step suffices. Usually works in practice. Okay. Okay. Now, alternating optimization for constraint problems. The alternative optimization methods can also be used for constraint problems like this. So you have minimization of f of x1 until xm. However, you have constraints too. xi belongs to some set si, each xi, right? So because you have m variables. Now we are talking about m variables, distributed optimization. So, and you have, for each of them, you have some constraints, a set of constraints, si. Si can be, this is a feasibility set, which can be made by some equality or inequality constraints. Therefore, what I mean is that for each variable, you might have a set of equality and or inequality constraints, right? Okay, now what do we do? In this case, every line of optimization is a constraint problem. See, argmin of these with respect to x1, subject to x1, because this is the optimization over x1. Therefore, we take care of the constraint of x1. x1 belongs to s1. Here, argmin of f with respect to x2, others are constant. Subject to x2 belongs to s2. And now, for each of these, you should use a constraint optimization algorithm, such as projected gradient method, such as Newton's method with equality and inequality constants, interior point methods. For each of these, you can do an interior point method. So something like that. Again, theoretically, you need to do it until convergence, but one step is usually works. Okay, any constraint optimization methods can be used. Practical experiments have shown that there is usually no need to use a complete optimization. Okay. Now, let's see other algorithms in distributed optimization. Dual ascent and dual decomposition methods. Why? I'm just building up to finally introduce ADMM to you, which is the state-of-the-art distributed optimization in the literature. And many papers and methods are using ADMM in them. You'll see that. Dual ascent and dual decomposition. These are the baselines which we build on to go and introduce ADMM. Okay, dual ascent method. Consider the following problem. Minimize f of x subject to ax equals b. Assume we have equality constraint, for example. Okay, let's use the method of Lagrange multipliers that we discussed. Recall the slides of KKT conditions and Lagrangian. Do you remember? What is the Lagrangian for this? F of x plus nu transpose ax minus b, where nu is a dual variable for the equality constraint, right? And nu is a vector here, because here we have several, you might have several equality constraints. This is a matrix times a vector, which is a vector. So we have several equality constraints. The dual function is this. G of nu is infimum or minimum of Lagrangian x and nu with respect to x. Recall the definition of dual function. The optimal dual problem maximizes this. This is a dual optimization problem. Do you remember? It maximizes G nu with respect to nu, where as it is not lambda, if we had lambda had to be greater than or equal to 0. Do you remember? However, it's nu. We don't care. We don't have constraint for that. Nu star is this argmax of G nu with respect to nu. So the optimal primal variable x star is this argmin of Lagrangian of x and nu star with respect to x. Okay, for solving equation 6, we should take the derivative of the dual function. This is a dual function. Take the derivative with respect to the dual variable. Do you remember? the method of Lagrange multipliers. So take the derivative of g nu with respect to nu, according to equation 5, is the derivative of infimum of Lagrangian with respect to x. The derivative is with respect to nu. According to equation 7, I'm putting it here. So what is the infimum of Lagrangian? Let me think. Oh, yes. So when you take the infimum argmin of Lagrangian is x star, okay? Therefore, I can put x star in the Lagrangian to get the infimum of Lagrangian. So here, f of x star plus nu transpose a x star minus b, right? Now, take derivative of if this term with respect to nu. This term is a linear term with respect to nu, which is ax star minus b, and this term is the constant, so it becomes 0. So ax star minus b. Okay. Now we found this. Nu star, we know that is argmax of g nu with respect to nu, and x star is argmean of Lagrangian of x nu star with respect to x. Okay. The dual problem is a maximization problem. Yes, we know that. This is a dual problem. Do you remember? This is a dual problem. Equation 6. It's a maximization problem. So we can use gradient descent for iteratively updating the dual variable with this gradient, right? Because for this, we solve this with any optimization algorithm such as gradient ascent, because as it is maximization, we need to do gradient ascent rather than gradient descent, right? Okay, we can alternate between updating. So that's the key thing here. We can alternate between updating the optimal primal and dual variables. So we want to solve this argmax of g and argmin of Lagrangian with respect to x. So we can alternate between these two because we have two variables here. Do you remember in distributed optimization, we have several variables. You have two variables, x and nu. Let's alternate between them. X k plus 1 argmin of Lagrangian, and then update nu in this way. We'll talk about it. So this is, I think this is normal. You might be wondering why we have equation 9. Okay, let's talk about it. K is the iteration index and eta is the step size. Okay, also called the learning rate at iteration k. Okay, equation 8. First, let's talk about equation 8. What does it do? It can be performed by any optimization method. This argmin of this. We compute the gradient. For example, we can do gradient descent or whatever. We compute the gradient of Lagrangian with respect to x. If setting this gradient to 0 does not give x in closed form, if it gives x in closed form, it's done. Otherwise, we can use gradient descent to perform equation 8 because it's minimization. So we can do gradient descent, right? And it's unconstrained. Otherwise, if it was constrained, then we had to do, for example, projected gradient method. But now it's unconstrained, so gradient descent suffices. Some papers approximate equation 8 by one step or few steps of gradient descent rather than the whole gradient descent until convergence. Again, the practical hint that I gave you. Okay, you can do one or several steps in practice. If using one step, we can write equation 8 as this. This is one step of gradient descent, right? Where a gamma is the step size or learning rate in the gradient descent for this. It has been shown empirically that even one step of gradient descent for equation 8 works properly for the whole alternating algorithm. Okay. So we saw that we had this. I'm repeating what we had in equation 8 and 9 here. We continue the iterations until convergence of the primal and dual variables. This convergence is important. We shouldn't do this only for one iteration. We should do it for the whole until this x and nu converge to some value, to stable values. When we get closer to convergence, that's the thing. Now I'm justifying the reason for this, or equation 9. Okay, so when we get closer to convergence, this becomes 0. Do you know why? Because the dual variable tries to satisfy the equality constraint, right? That's why ax should be equal should be equal to b. Therefore, ax minus b should be equal to 0. So ax k plus 1 minus b should converge to 0, so that we will not have update of dual variable according to equation 9. Equation 9, or here I have repeated it here. This means that after convergence we have this almost 0, this term. This becomes almost 0, so that the constant ax equals b in equation 4 is satisfied. Okay. In other words, the update of dual variable in equation 9, this, is taken care of satisfying the constraint. Of course it should, because it's a dual variable for the constraint, right? Now I think this is justified, why we have this update. So this is a linear combination of previous nu, a log of history, like we had in momentum, and some learning rate times the constraint. When the constant is not satisfied, especially in the initial iterations, the change is huge. Otherwise, the change we don't have any change. Nu k plus 1 becomes nu k. Okay, this method is known as a dual ascent. Why? Because it uses gradient ascent for updating the dual variables. This is gradient ascent. Do you remember? Because we are using argmax, and argmax can be done by dual ascent. It's similar. So this is very similar to what we have in gradient ascent, assuming that this is like a gradient. Eta gradient is like dual ascent, gradient ascent. Okay. Now we have another method, dual decomposition method. What does it do? Again, consider this optimization problem. Minimize f of x subject to ax equals b. If the objective function can be distributed and decomposed on b blocks or b variables. So let f be written as this. f1 x1 until f1 xb, something like that. Give me a second. I think there's no need for a 1 here. Sorry about that. Okay. Then we can have b Lagrangian functions where the total Lagrangian is a summation of these functions. What does it mean? Okay, let's write the Lagrangian for this optimization problem. What is it? The Lagrangian becomes f of x plus nu transpose ax minus b, right? Now, when we have fx1 plus if f of x is fx1 until fxb, so this Lagrangian becomes fx1 plus nu transpose, for example, ax1 minus b plus fx2. I'm rearranging this into this ax2 minus b until so on. So each of these, I call it Lagrangian li. I define it this. Therefore, I can write this Lagrangian as a summation of these li's. Okay. So in other words, I'm distributing the Lagrangian itself. Okay, we can divide equation 8. Where's equation 8? Here. Equation 8. This, I've repeated it here, into b updates, each for one of the blocks. So what was the question? This. So this argmin of Lagrangian, I can write it as argmin of Lagrangian. Sorry, this, I think this should be li. Argmin of li x nu k with respect to xi for all of the i's. So what this line is actually b lines. I'm just summarizing them in one line. Okay, so x1 k plus 1, x2 k plus 1. Okay, and then at the end we have nu, the update of nu, which we had in dual ascent as well. You remember dual ascent? Okay. So what is the difference between dual ascent and dual decomposition method? It's that we have b xi's, but in dual ascent we only have one xi, one x. Here we have b of them, so we have b Lagrangians. Now, so I've repeated what we found here. Okay, this is called the dual decomposition method, developed by decomposition techniques such as these: Dantzig-Wolfe decomposition in 1960, Bender's decomposition 1962, Lagrangian decomposition 1963. These are the papers which almost worked in this area. As you see Wolfe here again. Wolfe was a very important scientist in optimization. Okay. The dual decomposition methods can divide a problem into sub-problems. See, it is dividing the problem into sub-problems. Why? Here. So it divided the Lagrangian into B Lagrangians, B updates here, and solve them in parallel. Why? Because these are independent. X1 and X2, Lagrangian 1 and Lagrangian 2, these are independent of each other. So you can do this on B CPU cores, right? And then aggregate them and then do this. So do it on B CPU cores, then aggregate them and then do this step. What does it remind you? If you have some knowledge of machine learning, this might remind you of federated learning. In federated learning, you also have several servers. You send your solution to several servers, they do the computation, and then they aggregate it back. They do something, they average it again, and then they send to the servers again. This is usually distributed algorithms work like this. They have several servers or several cores or whatever, nodes, or several agents. They do the thing, and then we aggregate them, do something, we send them back again. They do their things, they send it back to us, something like that. Okay, usually this is the core idea between the distributed algorithms. Okay. Now let's talk about augmented Lagrangian method of multipliers. Okay, what is that? Recall equation 4. So that was the optimization problem that we were working on, right? Assume we regularize the objective function in this equation by a penalty on not satisfying the constraint. Do you remember? This is now let's have a soft penalty. So I'm adding this. This is not a hard penalty. If it was an indicator function, that would be a hard penalty. We talked about penalties in the previous session. So this is a soft penalty as a regularization term, and rho over 2 is just a regularization parameter. Although I don't remove the constraint. So this constraint is hard penalty, but I add the soft penalty as well. Okay, rho is a regularization parameter. Augmented Lagrangian proposed in 1969 is defined as this. If we form the Lagrangian of this problem 13, it is this, right? What is the Lagrangian of this? Is f of x plus, so this term plus this term is the objective function, and nu transpose ax minus b is for the constraints, right? This is exactly the Lagrangian for this problem. However, this Lagrangian is called augmented Lagrangian for this problem. So this is Lagrangian for this problem, but augmented Lagrangian for this problem. Why? Because we are augmenting something here. Augmented Lagrangian. Okay. So augmented Lagrangian is this. Recall equations 8 and 9. Where were they? Okay, I have repeated them here. Let's look back. For dual ascent, the equations that we had in dual ascent, I'm repeating them here. Right? Recall them. Now let's use this augmented Lagrangian in these two equations. So rather than Lagrangian, here we have, by the way, do you see the difference of notation? Rather than L, I am using L rho. So the rho is now the parameter of the augmented Lagrangian, right? So here, rather than Lagrangian, I'm using augmented Lagrangian. And what do I have here? That's the thing. The only difference is this, okay? Oh, no, there is a difference here. Here is we had eta, as a learning rate, but now I changed the learning rate to be rho. I don't want to have too many parameters, so I make this parameter the same as a parameter in the augmented Lagrangian. Okay, so now I have these two. Rho is the step size for updating the dual variable as well. We used also in the augmented Lagrangian. This method is called the Augmented Lagrangian method or method of multipliers, proposed in 1969. With the same paper, I think, yes, with the same paper which proposed augmented Lagrangian. Okay. So as you see, it's also a distributed optimization algorithm. Now, ADMM. All of these developed into a very important algorithm named ADMM, short for Alternating Direction Method of Multipliers. It's one of the state-of-the-art algorithms for distributed optimization. Oh, okay. Now, what is that? So, Alternative Direction Method of Multipliers, or ADMM, proposed in 1976, has been used in many recent machine learning and signal processing papers. The usefulness and goal of using ADMM and other distributed methods are twofold. Why do we use them? It makes a problem distributed and parallelizable on several servers. It makes a problem, it makes it possible to solve an optimization problem with multiple variables. When we have multiple variables, we can use ADMM. Consider the following problem. Assume we have two variables, x1 and x2. Minimize f1 x1 plus f2 x2, subject to ax1 plus bx2 equals c, which is an optimization over two variables, x1 and x2. The augmented Lagrangian for this problem is this. What is this? This is the objective function. This is for the constraint, and this is the augmented term, right? And when you rearrange this, this is inside the constraint. Do you remember in augmented Lagrangian, this was inside the constraint? Okay. Where were we? Here. So we can alternate between updating the primal variables x1 and x2 and the dual variable nu until convergence. Here, do you remember? Also in here in like in dual decomposition method, I said this line is B lines. Here now in ADMM that I'm talking right now, B is 2. So we have two lines, x1 k plus 1 arc mean of augmented Lagrangian with respect to x1, and this is with respect to x2. And this is the last term which we also had in the previous methods, right? Okay. This is ADMM. This is ADMM, but for two variables, but we will improve it in a few slides. Okay. This is the simplified. This is very basic ADMM. Note that the order of updating primal and dual variables is actually important. So the order of updating the primal variables, we don't care much. So if you change the order of these two, we don't care much. As long as you take care of the indices. But usually in ADMM, you need to update the dual variable at the end. Okay. It's important that dual variable, usually by practice, they have seen that. It should be updated after the primal variables. But the order of updating primal variables is not much important. Okay. A good survey or tutorial on ADMM is by Boyd, actually. It was published in 2011. Okay, so now equations 19 and 20, I mean these two, can be performed by any optimization method, such as gradient, calculating the gradient of augmented Lagrangian with respect to x1 and x2 respectively, and using a few iterations of gradient descent, for example, because these are argmin and these are unconstrained. So you can do a few iterations of gradient descent for each of them. In theory, you need to do it until convergence, but usually several iterations are enough for each of them. Now, let's simplify the equations in ADMM. The last term in augmented Lagrangian, equation 18. What was equation 18? This is the augmented Lagrangian. Do you remember? The last term, this. Let's simplify that. No. sorry, these two, these nu transpose this and this term, I'm repeating them here. Now let's simplify them. Okay, I'm repeating this here. I'm not doing anything complicated. So I'm repeating this also here, but I'm adding something and minus something. So plus something minus that thing again. These two can cancel each other, but now they can be used for simplification of this term. Let's see. So I'm repeating this. Sorry. I'm repeating this here. So this is not changed, but I'm using this here with them. So what am I doing is this. So this is repeated here, but I'm factoring out rho over 2. Therefore, this becomes simplified to 1 over 2 rho, which is here. So that's done. We also, this term is repeated here. These cancel each other, these and these. Also, this term is repeated here. This term is repeated here, right? So this is easy. And now I'm using this. Do you remember this formula? But for vectors, we need a squared L2 norm. Therefore, this term squared plus this term is squared plus 2 the first times the second, or when we have vectors, it's dot product, right? Therefore, we can say this. The first term, this is the second term, squared. And this is repeated here. Okay, that's easy. And what is this now? Let's see. Okay, I'm repeating this here again. However, I'm replacing 1 over rho times nu by u. I'm defining a variable named u. And I'm repeating this here. Okay, that's it. And now the last term, which is this, is constant with respect to the primal variables x1 and x2. That's an interesting thing. Okay, this became constant with respect to x1 and x2. And recall that we are minimizing the augmented Lagrangian with respect to x1 and x2. Therefore, the last term is dropped. So we can drop them from Lagrangian when updating the primal variables. Hence, the augmented Lagrangian can be restated as this. F1. So do you remember the first two terms in augmented Lagrangian, F1 plus F2, and we simplified these two terms here. So I'm putting them here, and this is a constant. Okay, now this is the augmented Lagrangian. For updating x1 and x2, the terms f1 x1 and f2 x2 are, oh, sorry. So for x1, when we are updating x1, again, recall that we are minimizing Lagrangian with respect to x1 and x2, right? When we are updating for x1, we are minimizing with respect to x1. Therefore, this f2 x2 is a constant. It can be dropped. For updating x2, this term is constant and can be dropped. Therefore, they are simplified. So the constant is dropped. For x1, minimization with respect to x1, this is constant and this is dropped here. So only these two terms are left. For x2, this is dropped. This is constant. This is also constant. They are dropped. So only these two terms are left. And we also had it before. By the way, recall that here we had nu, but I had a change of variable here from nu to u. That's why I'm updating u here. Okay. If you put 1 over rho times v as u and put it in this equation, it becomes simplified to this equation, equation 25. Okay, now, so we simplified ADMM to this. Okay, now, again, equation 23 and 24 can be performed by one or a few steps of gradient descent or any other optimization method. Not necessarily just gradient descent. And if sometimes in your problems, we might have constraints here. Recall here. Here, recall here, this step. If you have constraint, then you need to do, for example, projected gradient method. You need to do some algorithm for constraint optimization. Okay, the convergence of ADMM, if you want to see the proofs for convergence on non-convex and non-smooth functions, it has been analyzed in paper 12, reference 12. Okay, ADMM algorithm for general optimization problems and any number of variables. So ADMM can be used for general optimization problems and any number of variables. It can be extended to several equality and inequality constraints for several optimization variables. Recall that here we started with only 2 optimization variables, and we only had equality constraints. Now it says, let's extend it for several, more than 2 variables, and maybe we'll have inequality constraints as well. Okay, like this general case. Minimize summation of fi(xi) subject to this. Okay, so we can do that. We can convert. What do we do for inequality constraints? Similar to what we had in interior point method, we need to do some trick to get rid of the inequality, because the inequality constraints are really pain in the neck, like what we had in interior point method. We should usually do something about them, but we can handle equality constraints. But let's do something about the inequality constraints, like what we did in interior point method. Here, for example, we can convert every inequality constraint to equality constraints by this technique mentioned in papers 13 and 14. So these can be written as this, as another function equals to 0. So yi prime xi equals 0 is an equality constraint, right? But let yi prime xi be defined as a squared. This squared is for just taking easily taking derivative. Squared of max of 0 and yi xi. If yi xi is greater than 0, this becomes yi xi, which is not 0. Therefore, it can't be greater than 0. However, if it is satisfying this, if it is less than or equal to 0, this term becomes 0, because maximum of 0 and something less than 0 is 0, and this equality is satisfied. Therefore, using a good trick, we could convert this inequality constraint to equality constraint. Okay, therefore, the problem becomes like this. So the inequality constraints became equality constraints. So we had this. Now having dual variables lambda and nu, let these lambda be for these and nu for these. And the regularization parameter rho that we had for augmented Lagrangian. The augmented Lagrangian for this problem is this. So we have m variables. We have here, let me think. Yeah, I think it should be lambda and nu. So we have summation of fi(xi). This is the objective function. This is for these constraints, and this is for these constraints. And we also have these two as the augmented terms in the augmented Lagrangian. Okay. Here we can simply write them in the vector form or matrix form. This is the squared L2 norm. Also, I write these summations as a dot product. So I can say y prime x, I'm putting them together as a vector. Also, I'm putting hi's as a vector. Okay. Now, so we found this augmented Lagrangian. Updating the primal and dual variables are performed as this. So we have, again, this is m equations. I'm summarizing in one line. So x1 k plus 1, x2 k plus 1, and these things. So I'm arguing the augmented Lagrangian with respect to xi. And then each of these is just for one of the, these are for the inequality constants, which we converted to equality constraints. And this is for actual equality constraints, right? Note that the Lagrangian is completely decomposable by the I indices here. Therefore, the optimization for every ith primal or Dor variable does not depend on other indices. In other words, in the terms of the other indices become constant for every index. Now, that's an interesting thing. So like what we discussed before, here we said that, for example, for x1, f2, x2 can be dropped because it's a constant. We can do it here too. We have m variables, but for example, for x1, k plus 1, all of the terms which only have x2, x3, and so on are constant and can be dropped, and so on. So the last terms in the augmented Lagrangian, the last terms in the augmented Lagrangian equation 27. Here was the now I'm simple. Do you remember here? We simplified the last terms. Now I'm simplifying the last terms for this one. So here, what are the last terms? Okay, here. These, and these. Let's simplify them. I wrote these terms. If you write them together, okay, let's see. So I'm repeating this here. I'm repeating this here. Give me a second. I'm adding this, taking it out again. I'm adding this, taking this out again. And I'm repeating this here. And I'm repeating this term here. So it's the same. So I'm just adding this and minus this, adding this, minus this. Now, if you consider this term, and this term. So these three terms, put them together and factor out rho over 2. Repeat this here. Factor out rho over 2 and take these three terms. Repeat this here. That's it. Use the use this formula for vector form here. So the first term, the second term, a squared L2 norm, repeating this here again, plus rho over 2, again, the first term plus the second term, squared L2 norm, repeating this here. So now here, I have another change of variable, similar to what we did before. 1 over rho times lambda, let it be u lambda, change of variable. 1 over rho nu, let it be u nu. So I replace this with this with this, and this with this. And also these terms are constant with respect to x1, x2, x3, so on. So they can be dropped. Now I put those. So this was the augmented Lagrangian that we discussed. We simplified the last terms in the augmented Lagrangian, right? This was our simplification, which we discussed. Now let's replace this with this. So I'm putting this as instead of this. This is the augmented Lagrangian. Now the summation of fi xi rho. Okay, what I can write these element wise. So I can these are vector wise. This we can write it element wise by summation. And we have u lambda I. These are the ith elements of u lambda and u nu. The ith elements of the u lambda and u nu. It's almost done. This session. Let me finish this slide. This is the last slide in this session. So ADMM algorithm. Okay, what did we say? So this was the augmented Lagrangian. We came up to this point. I'm repeating it here. Hence, updating variables can be stated as this. So I can have for each of the m. So this is m lines actually. For each of them, I have this term. This is a constant and it can be dropped. By the way, this is summation of fi xi, but for xi, only fi xi is left. And the other terms are constant and can be dropped. Therefore, summation can be dropped, right? And so for x1, we have only f1, x1. For x2, we have f2, x2, and something like that. And we also have u for u lambda and u nu, we have this. But here we had them in vector form, but now we are writing them in element wise. Therefore, this is also m lines, m equations. This is also m equations. Okay. So we could use ADMM for general case optimization, which was here, with any number of variables, and also inequality and equality constants. So we can use ADMM to solve a general case optimization problem, which is distributed, which is decomposable and distributed. That's an interesting thing. The next session, we will continue ADMM, and we will go over other topics such as so I need to think about the order of things, but the topics which are left are meta-heuristic optimization, search-based optimization, non-smooth optimization, non-convex optimization. These things, but I need to think about the order of their presentation. Any question before we conclude the session? No?
No.
Great. Yeah. Did you like this session? What's your feedback about it? Okay, great. I'm happy that you liked this session. Okay, thank you very much, and
Yeah, it was good. Thank you.
thank you very much. Have a good night.
Thank you. Have a good night.
Have a good night.
Bye.
Have a good
Thank
night.
you.
Bye. Thank you.